Okay, in this video we begin our third unit. The third unit is on linear and exponential growth and decay. This particular co-rec video is focused on linear and exponential functions, an introduction to them, what they look like graphically, independent and dependent variables. So essentially your section 8A and 9A from your regular class, Math 143. All right, so I'm going to go through probably the majority of this set of notes, and it should be straightforward and hopefully somewhat a review for you in some cases. All right, so graphing consists of plotting points on a grid referred to as the coordinate plane. So that this grid that you see down here, this is referred to as a coordinate plane. The coordinate plane consists of the horizontal axis, which is known as the x-axis. So going across the horizon to the horizontal axis is your x-axis, and the vertical axis, up and down, is known as your y-axis. It should be noted that all ordered pairs are written as x comma y, so you always pick out the x value, then the y value in parentheses. In example 1 here, you've got 6 different points. They want us to write the ordered pairs that are associated with each of these points. So if we start here with A, its x value would be 4, and its y value would be 6. So we would say A would be the point 4, 6. B, B is down here. So x value would be -3, y value -4. I'll let you try C. Let's look at D. D is on the y-axis, so that means I didn't go anywhere on the x-axis, so my x value would be 0, and then I went up to 3 spots on the y-axis. E, over here, I did not go anywhere on, well, this time I did go somewhere on the x-axis. I went over -5 spots, but then I didn't go up or down anywhere, so 0 for your y-axis. And then F right here in the center, you didn't go anywhere on x or y. It's referred to as the point 0, 0, also known as the origin on a coordinate plane. They're also associated with the coordinate plane what are referred to as quadrants. So and it goes around counterclockwise. So this would be referred to as quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So like for example, point A would be in quadrant 1, point B would be in quadrant 3, point C here would be in quadrant 4. If it lies on an axis, it would not have a quadrant. Okay. And I say that because you'll hear me say quadrant in some of the videos, whether it's in the co-rec class or the regular class, and you mainly, because we're in this particular course, you mainly focus on real life scenarios. We're going to be mainly up here in this first quadrant because that's where things are positive. So, fact just below that, the scale of the x and y axis always need to be consistent, but they don't have to be the same. So you'll notice up here in the coordinate plane above, on the x-axis I counted by 2's, and on the y-axis I counted by 2's. We're just saying here that you have to be consistent, but it also is saying that I could count on the x-axis by 2's, and then I could go here on the y-axis and count by 5's, for example. What you can't do is start counting by 5's and then, oh, now let me count by 10's. That's not legal. Okay. We move on down here to example 2. They just want us to determine the scale of the x and y axis. So just, what is the x axis counting by? And so the easiest way I always think of it is just to look here at the origin here is 0, and then what's the space between the origin and the first tick mark, which in this case would be 14, and then you can eyeball and make sure, okay, well 14 times 2 is 28, so it's definitely on the x axis counting by 14s. On the y axis, starting here at the origin, 1 tick mark up is counting by 10s. And then it continues to count by 10s. And you'll notice that it does that, top and bottom, left and right. Okay. I'm going to flip it on over. Example 3 at the top of the next page wants us to graph these ordered pairs. I think I'll graph, I'm going to graph A, B, and D. Okay, and then you might want to pause the video and make sure you can do C and E. X-axis, y-axis. On the x-axis, I'll just count. Let's see. On the x-axis, I've got to get just kind of looking at my numbers, I need to be able to get out to 9. Can I do that by ones? Yeah, I can do that. So I'm just going to count by ones. 1, 2, 3. Make this pen a little smaller. On the y-axis, I need to be able to get to 10. I can tell this axis is not as long, so let me see if I can count by twos. 2, 4, 6, 8, 10. Yeah. 2. So remember, it's okay that, there are different scales just as long as they're consistent on that axis. So the x-axis is consistent by counting by ones, y-axis is consistent by counting by twos. So if I plot the point A, which is the point 1,8, I am right here, and I'll just put an A beside it. Plot the point B, which is -3, +10. So there would be point B. And then D would be -5, 0. So that's telling me to go -5 spots on the x-axis and then not go anywhere on the y-axis. And that would be point D. Okay. We'll move on down here. As I mentioned, we're talking about 2 types of growth and decay patterns, linear and exponential. Linear growth, the function grows by the same fixed amount per unit of time. Linear graphs are always straight lines. Exponential growth is the function grows by the same fixed percentage per unit of time. These will have a curved graph. Just below that, I've given me some space here to give you some, pictures of what linear growth and decay look like versus exponential growth and decay. So linear growth, and like I mentioned a minute ago, I'm going to just focus here on the first quadrant because that's what makes the most sense. You think about the example that I'm going to give you here is I'll put years on the x-axis and salary over here on the y-axis. And perhaps you started a job and you stay at that particular job, you get promotions over the years. What happens? Your salary increases. So as the years go by, your salary, we always say, hopefully increases. This is what I mean by staying in the first quadrant. Negative time would not make any sense. Negative salary down here would not make any sense. Okay. Linear decay. It's a coordinate plane, first quadrant. This one we'll look at age of a car. We'll just measure it in years. And we'll put its tax value. Well, as soon as you buy the car, it's up here, and then as far as when you first buy the car, the amount of taxes you have to pay on it is pretty high, but every year it starts to go down, right? Until at some point you no longer have the car. All right, and then you no longer owe anything on it. Let's look at exponential growth and decay. Do our 2 coordinate planes here. On the first one for exponential growth, I'm going to put time down here on the x-axis and population over here on the y-axis. This is just, an example. They don't, not all time and population always reflect exponential growth, but here's an example. Over time, perhaps the town or a city is experiencing a population burst, and that they are increasing at a rate of, I don't know, like 15% per year. So it's going to give you that curve. Versus up here, these were fixed amount. Like, for example, with our salary, maybe you were looking up and getting a $2,000 raise each year. Over here with your linear decay, maybe the tax office was decreasing the value of decreasing the value of your car, thereby your taxes were decreasing by, let's say, $50 per year, for example. Down here with exponential, let's say here, oh, maybe this is a 15% increase per year. Or maybe you drink caffeine in the mornings and then it starts to decrease out of your body at a rate of, I don't know, maybe 5% per hour, maybe. I don't know the exact rate that happens. I'll put caffeine level. So exponential growth over here on the left, exponential decay over here on the right. Okay. All right, we'll flip it on over then. Let's look at example 4. We want to determine if these statements reflect linear or exponential growth or decay, and then answer the associated question. So here in example 4, part A, it says the membership of a motorcycle club increases by 10 members each year. In 2010, the club had 45 members. How many members will the club have in 2020? So if you go back on this previous page, I'll just remind you of this. This is your key to knowing the difference between the two. Linear is always a fixed amount. Exponential is a fixed percentage. So make that distinction, whether it's an amount or a percentage. If it's an amount, you're linear. If it's a percentage, it's exponential. So here, we're increasing by an amount, 10 people per year. So that automatically then makes us linear growth. Now to figure out how many people we have, we know that we started with 45 members. We're going to increase by 10 members for each year, and you started this in 2010. They want to predict for 2020. How many years are we doing this for? That would be 10 years. And you could just put that in your calculator all at one time, and that should put you at 145 members. Okay. Move on down to part B. It says the number of houses in a rural town increases by 3% each year. If in 2018 there were 400 homes, how many homes will there be in 2020? If you're increasing by 3%, that's a percentage, that means then we are talking about exponential growth. I'm just going to abbreviate there. Exponential growth. Right now, you don't have a specific formula for exponential growth and decay, so we won't be we'll go ahead and calculate this, but I'm not going to ask you to do a problem that would have a lot of years to go by, usually just 1 or 2 years, because what we're going to have to do right now is rely on a formula that we had in the last unit, which was our original plus or minus percent times original equals your total. We're going to utilize that formula for now, but know that there is a better formula coming for exponential growth and decay. All right, so we'll start here with, we know that we originally started with 400 homes. 1 year later, it's going to increase by 3%, so you're going to put that 3% as a decimal, so 0.03. It's increasing by 3% of this 400. So we put that in the calculator, and that's going to give us the amount of homes that are there in 2019, which if you do that, you should arrive at 412. Now to get 1 year later for 2020 to get our final answer, so now you're sitting at 412, and you're going to increase by 3% of that amount. Last step, when you put that in your calculator, you should get 424. You get 0.36, so we're just doing nearest whole number, so 424 homes in 2 years. Okay. We'll look at part C. Part C says the amount of students in a school was decreasing by 2% every year. If in 2017 there were 2,400 students, how many students would be in attendance in 2019? So again, it's a percentage, so we know we have to be exponential, but you're decreasing this time, so that would be exponential decay. We'll still be utilizing the same formula. It's just that instead of using the plus sign, we'll use the subtraction sign. We know that we started out with 2,400 students. We're decreasing it by 2%, so 0.02 of that 2,400. We put that in our calculator. So 1 year later, we're sitting at 2,352 students. Get to 2000. So that would be essentially you start out in 2017. In 2017, you had 2,400. Here's your 2018 number, 2352. Now to get to 2019, we're going to take this 2352 and reduce it by another 2%. And when we do that, that should put us at, you get 2304.96, so round to the nearest whole number, so 2,305 students. Final answer. All right, and then lastly in part D, it says the cost of eggs were decreasing by 5 cents each month. If a dozen eggs cost $2.54 in January, how much could you expect to pay in June for a dozen eggs? So this is decreasing by a fixed amount, right? 5 cents. So since it's decreasing by this fixed amount, we're talking about linear again, but this time linear decay. So we know that in January we started at $2.54. We're decreasing by how much? 5 cents. Now you want to write 5 cents. Think about what 5 cents is. 5 cents is, you're not going to decrease by 5, you're decreasing by 0.05. Think about a nickel, right? A nickel is 0.05, so you're decreasing by 0.05. So don't think of that. I did not change that to a percent. I changed it to its value. 5 cents is 0.05. And we're talking about money. And then you're going to, so this is the January amount. You want to know, you want to predict the price of the eggs in June, so that would be 5 months later, because you would have February, March, April, May, June, so 5 months later. And then you could put that, like I said, in your calculator all at one time, and you should get $2.29. If you wanted to manually subtract 5 cents 5 times, it's the same thing, okay? All right, below that, the horizontal axis is referred to, as I said before, as the x-axis. And this is where your independent variables are plotted. Independent. The vertical axis is referred to as the y-axis, and this is where your dependent variables are plotted. This is, I kind of made a rough little segue there. This is actually starting section 9A here when we're talking about our independent and dependent variables. We need that terminology because as we move forward, we're going to be creating linear models, and linear models are made up of independent and dependent variables, and we need to be able to identify which is which. So the rest of this set of notes is talking about that. So independent are always plotted on your x-axis, dependent are always plotted on your y-axis. Below here in example 5, it says the graph represents the value, a depreciation of a boat's value over time. Here's the function. Here's your value equals negative 2,500t plus 27,500, and it's modeling this situation. Down below, they want us to identify the independent and dependent variables. Well, as I just mentioned to you that your x-axis is your independent, so we know that this is our x-axis down here, so this is our independent, and our y-axis up here is our dependent. I'm just going to abbreviate. So if we come down here, it wants us to identify our independent and dependent variable. Well, since they've got a graph sitting here in front of us, then they've kind of made it easy for us. Well, our independent variable is our x. So in our case here, that would be our time in years. Our dependent variable is our y-axis, and so that is the value of the boat. Now, if we didn't have this graph sitting in front of us, this part right here would be a little harder to figure out. Could be, potentially. This is where I always tell folks to use this sentence. The blank is dependent upon the blank. And these are your two variables, your value and your time. But whatever you put here in the first blank, you're saying that that's the dependent variable over here, and it's dependent upon your independent variable. And so think about this, if I were to fill in my dependent variable here, the value of our boat is dependent upon the age of the boat. Does that make sense? The value of your boat is dependent on its age, right? Over time, the value will obviously decrease. if you were to flip it around and say the age of the boat is dependent upon the value. No, it has to be that first way. The value of your boat is dependent upon the age. And anyway, that helps you identify your independent and dependent variables because, like I said, whatever goes here in this first blank is the dependent variable, and whatever goes in the second blank will be your independent variable. All right, let's flip it over to the last page and get a little bit more practice with that. I always tell you to utilize this sentence here. The blank is dependent upon the blank. Remember, first blank is your dependent variable. It's telling you that's your dependent variable. Second blank is your independent variable. I'm going to do the first four here with you, and let you get some more practice with this because I know this is one of the harder pieces of section 9A. The amount of fertilizer used on your grass compared to the growth of the grass. What I always tell folks is identify what are the two variables here. You've got the amount of fertilizer used, and you're comparing that to the growth of the grass. So if I'm utilizing my sentence up here, what's going to make the most sense? What is dependent? The growth of my grass is dependent on the amount of fertilizer I use, right? Because if I don't use any fertilizer, it may not grow too well. But if I use a lot of fertilizer, it's going to become lush and thick. Hopefully that's if it follows suit with what the bag says. So the growth of my grass. Growth of grass is dependent upon amount of fertilizer used. Look at B. The grade you receive on your math test compared to the amount of time you spent studying. So let's figure out our two variables here. The grade you get on your math test compared to amount of time you spent studying. So what's dependent? The grade you get on your test would be dependent upon your time spent studying. The grade you get on test would be dependent upon your amount of time studied. Let's look at letter C. The size of the apples in your orchard compared to the amount of pesticides used on the crop. So my dependent variable maybe even let me say this one wrong. Would it make sense for me to say that the amount of pesticides used on my apples would be dependent upon the size of the apples? Or does this sentence say better? The size of the apples would be dependent upon the amount of pesticides used, right? Hopefully you agree that sounds better and that makes more sense, that the size of the apples would be dependent upon the amount of pesticides used. And let's look at one more together. In letter D, the type of detergent used compared to the cleanliness of your clothes. So you would agree here that the cleanliness of your clothes would be dependent upon the type of detergent you used. A lot of times, you buy products and you say, well, that one doesn't work as well as this other one did, so you go back to that. So that's kind of like the idea here, is that the cleanliness of your clothes is going to be dependent upon type of detergent used. Okay. All right. Let me know if you have any questions with these. I know, like I said, that these can be difficult. This is this particular section here with identifying independent and dependent variables is important because, like I said before, as we move forward, we'll be creating linear models, and we're going to need to know which is which, so that you put the right variable on the x-axis and the right variable on the y-axis. All right. Let me know if you need anything. Thanks a lot. Bye.